Hey there everyone, welcome back to my YouTube channel. So guys, this is video 10 of our machine learning playlist, and in this particular video we'll be discussing about the different transformation techniques in machine learning. So there are mainly two types of transformation. One is function transformation and power transformation. In that again there are subtopics also which will be implementing the codes and discussing about those different transformations in detail in this particular video. So guys, what are you all waiting for? Those who all have not subscribed the channel, do subscribe the channel on the bell notification, and also feel free to connect with me on LinkedIn and also message me if you have any queries. So my LinkedIn link will be in this video description. So now let's not waste our time. Let's dive into my computer screen and discuss more about this particular topic. So guys, with the help of this particular article, you can see here, this one we have written this particular article. With the help of this, we'll be understanding in detail about data transformation techniques. So, and its types and even practical implementation also. Firstly, what is data transformation? Data transformations are like backstage artists prepared by the features. Let me just tell you easily. So for example, you can read this if you want, but let me tell you easily. For example, like you have an hero or an actor, okay, who is coming and acting in an movie. So you cannot expect him directly to come and directly act and go, right? So there will be many things. His hairstyle should be good, his dressing sense should be good. Then only he will be like an hero, right? I'm just telling you all an example. Like the same way, when the model is there, you cannot directly just standardize, normalize, and encode and feed that model, right? So there will be some different techniques which we need to check whether the data is nominal or whether it's left skewed, right skewed, or whether it's biased. We have to check many conditions and then we have to send the model to training, right? So for that, data transformation will be very helpful to us. Okay, why you need to use our data transformation? As I told you all normally, so for that, what is that the data should be normally distributed. So for that, you can see this image here. So how the data is normally distributed? So if the data is like this, normally distributed, and if it's skewed properly, and then you can like expect the training to be very good and you can expect the good accuracy. You can see here, so -3 +3, all the data is perfectly skewed and the same percentage and everything, both the left hand side and right hand side, it's equally skewed, okay, of a bell curve. You can take this bell curve as an example. So with the help of this, you can understand that if the data is properly skewed and properly good, then you can expect the good results. You can see here, we have written here also. The above image says that the data is distributed nominally and sometimes the data can be skewed also. Sometimes you can see this image also. So that is a nominal distribution here. With if the data is like this clear and crystal, then you can expect good accuracy. But some always you cannot expect the data to be clear and crystal, right? If it is clear and crystal, then why we need transformation? So for that, what it happens, you can see here. So positively skewed. In a sense, the bell curve you can see here. See, this is a nominal data, and you can see the bell curve is proper here. But when you come here, you can see this is positively skewed. In a sense, the left side the bell curve is more, and you can expect that the data performance also might be a bit slightly different, and even the model training also. So this is a normal symmetrical distribution. You can say it's equally distributed and negatively skewed. So right side, if it is more the bell curve, then it's negatively skewed. If left hand side it is more, then it's positively skewed. Okay, remember this, guys. Let's understand right skewed data. Mean. The mean is usually greater than the median due to the influence of the longer right tail. So you can see here the mean. This is the mean. So mean, median, mode, all are equally distributed at this particular symmetrical distribution. But here you can see the differences. Mean is here, median is after that, and mode is here. So you will be getting different values for that. That's all, nothing more than that. So now for left skew also it is a kind of same only. You can see here. Just try to read this, you will understand a bit more. Okay. Maybe this skew data is not good for model training. Why? Machines learn from patterns, and extreme values can mess up when the with the understanding when the data is not equally or nominally distributed. You're getting my point. So from first I was telling you all that only. So at that time, what we will be doing, we often tweak the data to make it more balanced and fair, and helping the machine learn better. So some of these transformations will help you achieve that particular balanced data. So they are mainly function transformations and power transformation. In this method, we will use the transformation of the data by using some mathematical functions. And here we will be using each data point with some certain powers. We will be using like power of the values and everything. We will be using that. So here the different things are log transformer, reciprocal transformer for function transformation, square transformer, square root transformer, and log transformer. Wait, again log transformer came. Okay, so 4 times log transformer, square and square root transformer until here. Okay, this is a mistake. Why log transformer? The purpose of log transformer is to reduce the impact of extreme values and make data more interpretable and suitable for certain types of analysis and modeling. So for that, the formula is log of e of x. Y is equals to log of e of x. E is the mathematically constrained approximately equal value. E is nothing but equal value, approximately equal value. Okay. These transformations make our data close to a nominal distribution, but not able to exactly like do nominal distribution. Means this only this transformation, whatever it is there, right? Log transformation, it can bring you close to that, but you cannot expect it to completely make it perfectly done. So this transformation is not applied for those features which have negative values. This transformation is mostly applied for right skewed data. Okay, now getting my point. So whatever is in your positive side, right, for that we will be applying this transformation. For negative transformations we cannot use log transformer. Okay, so the code is available here, and the same code you can have a try about this code, and also we have a detailed explanation of code also. Let me first complete this. Reciprocal transformation. In the another technique of the transformation that involves converting the non-zero data or x points into a reciprocal, that is 1 by x. So which is of non-zero, that will be converted into reciprocal form. Simple, the formula is y is equals to 1 by x. That's all. If a feature contains larger value, taking the reciprocal can help scaling them down. Okay, so in a right skewed distribution, most values are small. Taking the reciprocal can spread out the small values and bring them closer and together. So you're getting my point. So this is also kind of mostly applied on right skewed. So the transformation is not defined for 0. So this is not okay for 0, and we cannot apply it for 0. It is only applicable for your non-zero values. Okay. This transformation reverses the order among the same sign. If x is a small positive number, its reciprocal will be a larger value, and vice versa. Okay. So it will just reverse the numbers based on their value sign. Okay. So here this is the code for that. You can execute this and see. And square transformation and square root transformation. Let us complete this and I'll start to execute with the Google Colab. Okay. Square transformation. This technique involves in converting the data point x into the square root. Simple squaring. 2 square, 3 square, 4 square will be having, right? Simple. And even the formula is also y is equals to x square. That's all. Nothing more than this. So remember this point, this technique is applied only for the left skewed data. So above, those two techniques were used only for right skewed data and not for left skewed data. This is used for left skewed data. Okay, remember this. When you apply this technique, squaring on negative values will result to the positive value. So when we apply for negative values, whatever it is there, right, when it squares, it become to the positive value. Okay. However, it is important to note that the squaring of a small negative values will rise of its higher positive values. Okay, so remember this. and simple code snippet for this also. Now let's you can have a look on this. Just try to execute this. Until now, if you are seeing, you will be able to execute it. You will be able to understand this topics. Just make sure execute and see, okay, of this code, and we'll be practically implementing also with the data set. Okay. Square root transformation. This technique involves taking the square root of each value in the data. So applying the square root. So formula is simple. Square root of x. So here we used to square the values simply, but here we will be applying square root. Here you can see after applying these things, right? You can see here original data minus 3, minus 2, 1, so on. Squaring 3 3s are 9, 3 square 9. So 2 square 4. All the negatives are into positive. So 1, 4, 9. You got it in a kind of order value. You can see it is nominally distributed here. The data is 9410149. You can see the output. This is for squaring, but this for square root. Okay. For this, what it happens? This transformation is beneficial. Okay, it's my mistake. This transformation is beneficial when dealing the right skewed data and a few extreme outliers. When the data is having some extreme outliers, larger outliers, and it is beneficial for right skewed data. Both squaring and square root is for right skewed data. So taking the square root can help compress the large values and make the distribution more symmetric. So formula is simple: square root of x. Remember, this square root is this transformation is defined only for positive numbers, not for negative numbers. If negative numbers, it will become weak. This transformation is weaker than log transformation. So it is more weaker than log transformation. This can be used to reduce the skewness of right skewed data. Only to reduce the skewness, we can use this particular formula. So you can see here square root of this particular 4 is 2, square root of 9 is 3, 4, 5, 6. You can have execute this and try to understand this code. It's easy and you can easily understand. Now let's go to the coding part of this particular functional transformations. Okay, so first let us start with log transformation. So import all these necessary libraries. You can see here all this metrics. So pandas, numpy, skypy, from skypy.stats import qqplot. We are importing qqplot for better visualization. From sklearn model selection, train test split, accuracy, cross validation, logistic regression, decision tree. So we'll be using all this column transformer and function transformers. So we have imported all this. So we'll be applying on Titanic dataset. Okay. So let us load Titanic dataset from SNS. You can see here it consists of three things. One is survived, age, and fair. So now checking null values. So there is null values in age. After that, what we have done? So always dropping the null values is not a good way. When you have very less null values are there, you can drop. But here you can see 177 features you might lose if you drop. So what we are doing, we are just filling the null values with mean. So after this, what you have? Then we have performed train test split. So age and fair is your training data and target y variable is survived, whether that person is survived or not. So now we will be plotting the data with qqplot. You can see here age, so PDF and qqplot, you can see the difference. So you can see the visualization. Ordered value here and theoretical quantiles you can see here. And then for fair also we are plotting the qqplot. Same. You can have a look on this graph for better visualization. Then what we are doing first, without any transformations, without applying any log nominal or any transformations, let us train and let us check both logistic regression and decision tree accuracy. You can see here in accuracy before transformation for logistic regression is 64 and for decision tree is 67. Now we are applying log transformation. So guys, here you can see transformation is equals to function transformer dot is equals to np dot log p1. So we are using log transformation here. So if you don't want log transformation, or you can use rec. If you just type rec np dot, you can see here reciprocal transformation. So you can select reciprocal transformation. You can try with that also. Or if you want np dot skew square skew, if you type square and wait, you will get see square transformation square. You can use square root also, you will get here. So I'm using log transformation here only, log 1p transformation. Now so we have transformed the data, so we have done some transformations. Okay, so after transformations what we are doing, so this is run, right? So x train transformed and y train transformed data are there, right? So we are now just feeding that data here, and you can see once you perform, see if you see without transformation 64 accuracy, and after transformation for logistic regression it's 68 accuracy, and for this decision tree it is a kind of same only 67 67. There was no much difference. So you can see there is an increase in accuracy. This is a small data set and it's a sample data set, so you can see very less accuracy. But when you perform in a high larger data set, you will see more accuracy. When we'll be doing a live project, right, you will understand a bit more detail about this. So now we can perform cross validation also. So for cross validation also we are performing transformations. And now if you check, see 65 it dropped down for decision tree and 67 for logistic regression. Okay, so now let us plot this before log transformation and after log transformation. So you can see before log transformation, fair, you can see a fair price. After log transformation it has been skewed properly. Okay, and you can see the distribution is properly done in this graph. So QQ plot will help us understand a bit more better in this way. Before log transformation age and after log transformation. So you can even see that there is no use of applying log transformation on age column. Okay, that's all. I hope you got this. And now what we are doing, now we will choose only fair. So we are applying only for fair the this one log transformation, and we are running that. So again we have checked the accuracy. Now you can see the accuracy is a bit better when we don't apply for age that particular transformation. So even to which column you have to apply the transformation, that also matters. Remember that, guys. Okay. So here you can see if you want to create a custom function also you can create here. So def apply transformation. So we have taken that and we have created a custom function here, log transformation. And finally we are checking for fair. Again, if we, this is a code for custom transformation, you can have a look on this and apply transformation np.sign. So when we use np.sign, it is applying the transformation. You can see here there is a kind of no more difference before and applying after applying the transformation. You can see here for fair. So as I told you all earlier, you can see here, so you have to just change this particular thing, np.square, np.reciprocal, and the place where I already showed you all, right? And there if you just change it is enough, sqrt square root and square and reciprocal, and if you try you will get it in more detail. Just I recommend you all to have a try and explore all these particular methods. So for this particular function transformation, right, I'm just explaining you all log transformation. Just give a try on other three topics also. This is your task. Now let us move to power transformation. So in that there are mainly two types. One is box-cox and one more is Johansson transformation. Okay. Box-cox is a statistical technique used in machine learning to stabilize the variance and make the data more closely approximate for nominal distribution. So this is the formula for box-cox. It's a technique. Okay. So we can use this particular technique and we can bring it a kind of nominal distribution. This is particularly useful when we are dealing with data that exhibits heteroscedasticity, in essence, unequal variance across different values of the independent variable or non-constant spread. So at that particular time, we can use box-cox. Okay. So you can see the formula here for this. This is the formula for the box-cox transformation. Y representations represents the original variable, and this is for the transformation parameter. Okay, so just try to understand the formula, and you have a code for this also. This is a kind of generalization that includes square root, logarithmic, and reciprocal transformation as special cases. So this already includes all these three. So you can directly use box-cox transformation whenever you want instead of using all those three and trying different methods. So here you can see the code. So this is the formula. Just try to execute this formula. Using this formula, you'll get it a bit better way. Okay. Johansson transformer. Johansson transformer is an extension of box-cox transformation designed to handle both positive and negative values. So what box-cox will do, it can only handle positive values. But when it comes to Johansson, right, it can handle both positive and negative values in the data set. Similar to box-cox, the Johansson transformation aim to stabilize the variance and make data more systematic and bring it close to the nominal distribution. So the formula for this will be, you can see here, this is the formula. And try to understand more in a kind of coding point of view, okay, and more than a mathematical point of view, because you will be applying all this in coding point of view when it comes to your data set. Try to understand that mathematical formulas are important, but if you try to understand that, it's a good great and go, or else you can try with them already, because these all are already pre-built one, right? You can see a box cox and everything. You will be just importing from SkyPy. So this is the collab notebook. Let me connect with this. Yeah, there are many sessions running. Okay, function transformation also. Yeah, let me connect this now. So just understand more in a kind of coding point of view, so that you will be able to understand a bit more in detail. Don't worry, I know you all might be feeling more confused right now. When you perform one complete project from basic EDA to complete model training and execution, you will get everything in detail. Okay, let it to run. We are importing the necessary libraries now. And then what we are doing, concrete strength dataset. So we are taking concrete strength dataset for this. So I'm taking that dataset from GitHub. You can use that URL to get that dataset, and you can see here cement and blast funk stage and fly ash, water, and fine aggregate age and everything is there of that particular cement data. You can have a look on this data in detail. So info and describe. You can even see this describe. This method shows you the maximum value, minimum, and standard deviation, mean, and count of everything when you run df.describe. So you'll get it easily. So if you check df.isNull.sum, you will see that there is no null values. So we can directly go for training method. So using this particular one. So drop concrete comprehensive strength, because it is in input feature, we don't want that, and that is our target variable. Okay, we are dividing it into x and y, and we are doing train test split here. So I know you are not getting train test split, that we'll discuss more in our upcoming articles. Just try to understand about this here for now enough. So X-train, so it has been done. So what we are doing, applying without any transformation, you will see the L2 score as of 62 percentage of the accuracy you can see here when used linear regression. We are using linear regression here. Why? Because this is the kind of linear continuous numbers and values, and it doesn't contain any categorical data. So we are using linear regression. Okay. So box-cox transformation. Now what we are doing. So with box-cox transformation, if we apply, what it happens? See now. So plotting the disk plot without any transformation. So still we have not done any box-cox or any transformation. Without transformation, you can see the data kind of skewness and everything here. Just bring it here. You can see the data, however it has been distributed and there is no proper skewness here. So what we are doing now, we are applying the column transformations are right skewed and some are left skewed and some are nominally distributed. So after applying box-cox, you will see that it has been like a kind of nominally distributed. Now again, if you would perform the training the data and if you perform the accuracy, you will see now the accuracy is 80%. From 63%, it has drastically improved to 80%. So this is the main advantage of using transformation. Okay. Using cross validation score. So we have applied that, right? So now we'll check the cross validation score has increased to 66% now. So now what we will be doing, we will be again checking this. Now you will see that it is a kind of properly distributed. This is before and this is after. No, no, no. Both are before and after is not there, but it's the kind of, so you can see here the graph, it is like a nominally distributed. See the difference? Transformation helped us like kind of bring the model a kind of a better like accuracy. It can help you improve the accuracy. Just understand that. Okay. So now let us apply the Yo-Johnson transformation. You can see here 68% is accuracy after applying Yo-Johnson transformation. So let us run this. So plot, these plots are a kind of before and after comparison of Yo-Johnson transformation. You can see here before the data and after data, you can see the comparisons properly. It's easy to understand when you perform with coding and graphical visualization and trying to understand mathematically. Okay, remember this. You can see the lambda of each column on both the side in the box-cox and Yo-Johnson. Okay, so if you run this and see, you will see this. Okay. That is why we use this particular box-cox and other transformation methods. So now there are some more things left out. So we will cover in the next article, part 2 article, where there are only two more transformations are left out. Let us see them and we'll move further with train test split and other training methods this time. Okay. So guys, that's all for today's video. Do like, share and subscribe the channel. Thank you all. Bye bye.